Thank you very much for being here, and we have the great pleasure of presenting our special guest, Luca De Feo. Luca De Feo is very famous, so I don't need to say many things about him. I will say only the essentials that, as you know, he is considered, along with David Yao, one of the inventors of psych. That I guess he is going to talk about it. And today is going to talk about isogeny-based cryptography, as was promised in the abstract. So, Luca, thank you for being here. It's our great pleasure and honor, and the floor is yours.
Thank you very much, Francisco, for the introduction. Thank you very much for the invitation. Spent 2 very interesting and fun weeks here in Abu Dhabi, and it's a pleasure being here. And thank you all for coming. Thank you, people on Zoom. Please take seats. Be careful with the cables. So I think I promised to talk about isogeny-based cryptography, or what's left of it, because if you have been following a little bit the news in post-quantum cryptography, you heard that something important happened this summer. And so my goal today is to convince you that you should really try and understand what's this something important that happened this summer. I will start from the beginning, in a sense. So I will start from analytic curve. Because this is where isogenies come from. Isogenies are a part of the theory of analytic curves. Raise your hand if you've already seen an analytic curve in your life. Okay, wild analytic curves roam in the streets of Abu Dhabi. If you've never seen one, I saw some non-raised hands. This is an analytic curve over the real numbers. This is definitely not what you use in cryptography, but at least this is something you can draw and kind of remember the shape. And the only thing I need here is remember the shape somehow. An analytic curve is a curve, as the name suggests. It's not an ellipsis. It satisfies a cubic equation, usually written in this form: y squared equals x cubed plus ax plus b, where a and x are parameters. And so you can choose among all these analytic curves, and they have different properties depending on which A and B you choose. Why analytic curves are so important? Because they're cubics. According to Bezout's theorem, every line is going to intersect the analytic curve in exactly 3 points, counted with multiplicity, if the finite field is algebraically closed. But yeah, just let's say exactly 3 points. And so you can see here, I drew a line that goes through P and Q and R. And what's very tempting is to try and define a set of equivalence classes of points, like groups of points, putting points together, set some rule saying that 3 points on the same line sum to 0. And see whether this gives some group law, in the sense that I can say sum. And it turns out that, yes, this is a fairly standard theorem in the theory of analytic curves. It wasn't invented by cryptographers. There is a group law defined on analytic curves, which you can geometrically visualize as, if I want to sum 2 points P and Q, I will take the lines that passes through them. I will intersect in a third point. And since I decided that P plus Q plus R is equal to 0, this means that some other point related to R must be P plus Q. And it's written in this form. It's nicely this point here, the opposite with respect to the x-axis, that turns out to be P plus Q. So you have a very simple geometric definition of how from P and Q you derive P plus Q. And you know, this is the beginning of elliptic curve cryptography. From this, you start analyzing the group law of elliptic curves. What are its properties? Interesting properties that it's abelian. And when you have an abelian group law, you start thinking, oh, maybe I can do Diffie-Hellman, if you know Diffie-Hellman. People quite quickly thought of using elliptic curves to generalize Diffie-Hellman. And now you know that this is an old story. Every day you use elliptic curve operations, like this kind of additions, like you do these computations with points. You don't do it by hand. Your mobile phone, your laptop does it for you every single day, millions of times, because this is what session establishment in TLS is based on, usually. It's either RSA or elliptic curve cryptography. And now Probably you already know how the story goes. Like this is we all signed to tell this little story. In the 90s, Peter Shor came with an algorithm that ran on quantum computers, lets you solve the discrete logarithm problem for any group, including the group of elliptic curves, of any elliptic curve, which means that the cryptography that I'm using today, it's in danger as soon as quantum computers become powerful enough. Raise your hand if you never heard this story. Yeah, that was my guess. And so this was a motivation to look at other. We didn't need that motivation. We've always been looking at other ways of doing cryptography, but certainly it was a very good motivation for us for asking for money, for looking at other forms of cryptography, and for investing lots of development efforts in making the other forms of cryptography practical and usable. And so you've heard about lattice-based cryptography, you've heard about code-based cryptography. These are all other branches of cryptography where you can define signatures, encryption schemes, key exchange schemes, where, as far as we know, no quantum algorithm breaks the basic problem in polynomial time. And among these families of problems of, we would say, algorithmic topics that we consider being suitable for post-quantum cryptography, there are isogenies of elliptic curve, which sounds a bit strange because I just said that elliptic curves are broken by quantum computers, and now I'm saying that isogenies of elliptic curves are not broken. And you will see that, of course, isogenies are related to the group flow of an elliptic curve because they are just part of the matter, but they are not based on the discrete logarithm problem. They're not based on the problem of given a point and given x times the same point, find x. It's not a discrete logarithm problem that we will work with. And actually, it will turn out that all the discrete log problems that you encounter when you do isogeny-based cryptography are usually easy discrete log problems, and that's used to do the computations in reality. So what's an isogeny? Because I already said the name, but I didn't say what they are. An isogeny is any of these definitions. You may choose the one you like, but probably the easiest one to remember is an isogeny is a morphism of elliptic curves in the sense of a morphism of groups. We said that elliptic curves have a group flow. A morphism of groups is a map between two groups that preserves the group structure. So isogeny of A plus B is equal to isogeny of A plus isogeny of B. This is an easy definition. This is not enough. You want the morphism to be algebraic. That's what you need to add, which means that essentially it has a geometric interpretation. That's what you want. An elliptic curve, an isogeny is not just any group morphism. Is a group morphism that you can, if you were to spend a lot of time, draw in pictures like this. Naturally, I can. Here is one picture. Here are two elliptic curves, not over the real numbers this time. They are over F11, the field with 11 elements. So there's only a finite number of points in F11 cross F11. So these elliptic curves have only a finite number of points, and they do not look at all like, not much like the one you saw before, but still, you can see at least they are symmetric with respect to the x-axis. There is some familiarity. So this is the curve y squared equals x cubed plus x. This is y squared equals x cubed minus 4x. And, well, this is not drawn this way, you don't see the geometry, but actually the geometry is here. This is an isogeny. This map here that maps x and y to x squared plus 1 divided by x, and y times s squared minus 1 divided by x squared. This is certainly a map that has a geometric meaning because it's just polynomials, rational fractions, mapping points on one side to the other side. And this turns out to be a group morphism. So it is an isogeny. This is the simplest example of isogeny you will see today. This is what we call an isogeny of degree 2. Remember this name, the degree. You read it here, essentially. The degree of an isogeny is roughly the degree of the polynomials that appear when you write down the isogeny. So. Yeah. If the field is algebraically closed. Yep. Thanks for picking me on these approximations. Indeed, like if you stare closely at these things, we could spend already the whole hour looking at this picture and picking all the details. This map doesn't look surjective at all, right? This map has some points that have no preimages. So this seems to contradict the fact that the morphism is surjective. What is not written here, what's implicit in this definition, is that I'm talking about elliptic curves defined over algebraically closed fields. So actually what you're seeing here is not very different from considering the map that sends x to x squared in the multiplicative subgroup of a finite field, for example. So what's the inverse of this map? What's the pre-image of the map x squared? Well, it's the square root. Does every element in a finite field have a square root? Certainly not. There are elements that are non-squares in a finite field. But if you go to the algebraic closure, every point, every element of a finite field eventually gets exactly 2 square roots. And this is what happens here. These are defined over F11, but if you go to the algebraic closure, then these points will start having preimages. And each of them will have exactly 2 preimages. There are some other weird things we can look at this in this figure. This point in red is not sent to anything on the right, because this is a generator of the kernel of the elliptic curve. This is a group morphism, so some points are sent to 0, to the identity element of the group, and the identity element of the group is not pictured in these pictures because it's the famous point at infinity. If you've already studied the elliptic curves, you know that there is this strange point which you cannot draw, at least not in this way. And so I just didn't draw the arrow because I couldn't have pictured, but you must imagine this point as being sent to the identity element of the group on the right-hand side. And also the other element that is sent to the identity element is the identity element of this curve, which again, you don't see. There's 2 extra points. There's 1 extra point here and 1 extra point here, which we're not drawing. So this picture is not exactly accurate. Understanding what the kernel of an isogeny is essentially the same thing as understanding the isogeny itself. So usually, and like just ask the guys here, ask Francisco, we spend all our time manipulating these points of elliptic curves and understanding what isogeny is associated to this point by the rule, okay, I take this point and I decided I want the isogeny with this point in the kernel. This is what we mean by computing isogeny in general. It's given an isogeny, find its kernel, given a kernel, find the associated isogeny. These are the easy computational tasks that we do all of the time and that we spend a lot of energy benchmarking. Any other questions on this? Yeah, I forgot to mention, don't hesitate to stop me and ask questions because, yes.
Is the kernel generated always in, let's say, here in F11?
No, you could have, yeah, you may not see it. And this is actually also a very, like, if you want to go, it may happen that the kernel is not defined over F11, but the isogeny itself, the rational maps, they are defined over F11. This is something that can happen, actually happens a lot of times, and that we use it too. So yeah, you don't necessarily always see it if you don't go to an algebraic extension. Other questions? Okay. So this is as much mathematics as I wanted to talk about today. I won't give you much more than this. Why isogenies in crypto? Where did it start? How did it start? Why people started looking at these strange objects? What's the motivation? It started in the 90s for cryptography, and the first motivation was counting points of elliptic curves. So you know that if you want to do Diffie-Hellman style cryptography, you need to work with groups of prime order. And it's actually difficult, not so easy, not so obvious. If I give you an equation for an elliptic curve, y squared is equals x cubed plus ax plus b, to understand how many points are defined over the finite field F11, for example. Here you can count them. These are what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 points, because you must count the extra point at infinity. So these are 12 points, but if P is large, like some 256-bit prime, then like you're not going to count them one by one, right? And so the first motivation was to imagine algorithms to compute the number of points on an elliptic curve. And usually the thing you do to generate curves in elliptic curve cryptography is you take curves at random, you count points, and you hope that their order is a prime. There's a good chance that this happens, and if it happens, you're happy. And the standard algorithm to do this, it's called Schroff's algorithm. It was invented in 85 or 84, 85, around that time. And then successive refinements by Atkin, Elkis, and many other contributors introduced the theory of isogenies in Hopf's algorithm to accelerate it. So the thing that now you can take SAGE, for example, SAGE Math, or ParisGP or Magma. You can launch it and give an analytic curve and then ask cardinality, and it gives you the number of points. It's actually running a very complicated algorithm that's using isogenies underneath. So this was the very first motivation, and this is how cryptographers first encountered isogenies. And then pretty fast, they started thinking, well, but isogenies are group morphisms. A group morphism means that I preserve the group structure. So if I have an elliptic curve and I have an isogenous elliptic curve, should mean that I can transport the discrete logarithm from one curve to the other. And so maybe if I choose the isogenous well, I can affirm that the discrete logarithm is as easy on one curve or as hard on one curve as it is on the other curve. So the very first application in theoretical crypto of isogenies was reductions, problem reductions, where you show that a set of elliptic curves in the same class all have the same difficulty for the discrete logarithm problem. And this is what essentially gave birth to the study of isogeny graphs, because now you can ask, okay, what is the, like if I have a set of elliptic curves and I try to connect them using isogenies, can I find the path made of isogenies between two elliptic curves so that I can reduce the discrete logarithm from one to the other? And so this naturally defines a graph. I'm going to show you some examples later. And so in these graphs, you can move the discrete logarithm problem around. And this is also what made cryptographers start to realize that finding isogenies between elliptic curves is not necessarily an easy problem. It's usually quite hard. And so if you find a smart way to use it for cryptography, maybe you have new systems which are not based anymore on the discrete logarithm problem. So this was the 90s. So you remember haircut on the sides, baggy pants, and isogenies in cryptography. But then, yeah, we came at the turn of the century, and people really started saying, hey, because it seems to be hard to compute isogenies in general between elliptic curves, let's try and make crypto. So the very first published proposal was by Charles Goran and Lotter in like January or February 2006, where they say, well, one easy thing we can do, it's hash functions. Sure. Obviously, hash functions are not the super duper, super complicated public key primitive, but still it is quite nice that by using some well-chosen isogeny graphs, and precisely the supersingular L isogeny graphs, you can define a hash function which essentially corresponds to do a pseudo-random walk in these graphs of isogenies. And then the difficulty of breaking the hash functions, for example, the difficulty of finding collisions for the hash function, or the difficulty of finding preimages of the hash function, is related to some very nice to state number theoretic problems on isogenies of elliptic curves. So this was the very first published idea. And soon afterwards, in unrelated and independent work, Rostov and Stolbunov published something that's really public key cryptography, and that was a key exchange scheme based on a very special class of isogenies and elliptic curves. Now, this is a bit complicated. I will come to introduce the terms better later, but the idea is that you have something that almost looks like the operation of exponentiating in a cyclic group. So this is the operation that you do when you do Diffie-Hellman, right? You take a generator and you do generator to the power A. That's what Alice does. Generator to the power B, etc. And so this group action is a generalization of this idea of having an exponentiation operation. And so by using this intuition, they define a Diffie-Hellman-like scheme where instead of multiplying points in an elliptic curve group, you shuffle around elliptic curves using isogenies. Immediately after Rostov and Stolbunov published their idea, people realized that Couvaigne had presented that idea 10 years earlier at seminars in Paris. And it turns out that Couvaigne had essentially the same idea, submitted to crypto, was rejected, and forgot about it, put in a drawer. So actually the very first isogeny-based scheme dates from 97 by Couvaigne, and it's exactly the same idea, but it stayed confidential, only known to a few people until that time. So this was the beginning, but at that time, this was all theoretical stuff. Like this scheme certainly wasn't easy to implement. It still isn't easy to implement today. We don't know how to run this in less than a few minutes. A key exchange that runs in minutes is not something that you can realistically use. This one, well, you could, first of all, it's been partly broken, so you need to apply some fixes, which, okay, you could. But what's the point of having a hash function based on these complicated problems? SHA is perfectly fine. But this is arguable. This is something that exists. And then we came to a turning point that Francisco just mentioned, 2011, SIDH. So SIDH was a work that I did in collaboration with David Zhao when I was a postdoc at Waterloo. David had this intuition that like this key exchange is very nice, but it's not efficient at all. Plus, there are some issues that I will discuss soon on the quantum security on this key. This idea is very elegant, but it's only a hash function. Is there a middle point? Is there a way to combine the two ideas and get a key exchange from supersingular isogeny graphs? And the idea is not straightforward, and I will not explain it because today there is not much point in going into the details of this idea. But it was really the very first isogeny-based scheme that was efficient, that you could run in practice. So the very first implementation ran in 4 seconds. And then after a few months of work, we got to something that ran in 30 milliseconds. And then it kept improving and improving until like the recent years, where this was made into a candidate to the NIST competition called SIDH, which could perform a key exchange in 10 milliseconds. Now, if you come from lattice-based crypto or from code-based crypto, you will not be impressed by a 10 milliseconds key exchange speed. Like you are more likely looking at 10 microseconds for a key exchange. But the selling point for SIDH was that among all schemes submitted in this competition, it was the one with the smallest public keys and smallest ciphertext by a decent margin. So that's always been the selling point, and it still is the selling point of isogeny-based crypto. It is low, it is complicated mathematics, it's very hard to grasp, to the point that even the experts do not grasp it and then are surprised when it gets broken. But at least it has small keys, which may be useful for something. I would argue that small keys and small things are more useful for signatures than for ephemeral key exchange. So I'm more excited about what's to come than about than what I was excited for SIDH. But this certainly was a turning point because it showed to the world, or to the community, not the whole world certainly, that you could do isogeny-based cryptography in a usable way. And people started taking notice and started thinking more, and that's what has developed a community around this topic. So even though we can all have a funeral celebration for SIDH today, it certainly, we shouldn't understate the impact that SIDH has had on the whole field. And that's not just because I invented it. So in recent years, the field really exploded with new constructions, new ways, new ideas on how to do elliptic curve isogeny-based cryptography. And so it started really, another important turning point was 2018, when Wouter Kastrick and co-authors published CSIDH, which does not stand for Kastrick SIDH, stands for commutative SIDH. And this is essentially the same scheme as Kuveni, Rostov, and Stolbunov, but instead of using ordinary curves, they found a way to use supersingular curves, which was a surprise at the time, quite nice trick. And the main argument for this is that unlike Kuveni, Rostov, and Stolbunov scheme, this one you can implement it efficiently. And here in the room, you have several experts who know how to implement it super efficiently. So you can ask them all the tricks on how to do it. A few other ideas came in those years, like 1 year later, we realized that isogenies combined with elliptic curve pairings seem very suited to do something that's called delay cryptography. This is a branch that's completely orthogonal to post-quantum cryptography. These schemes are not post-quantum because these schemes are based on the discrete log problem, but they have other nice properties that are especially attractive to people who work on blockchain, I would say. 1 year later, and this is now the herald of isogeny-based cryptography, I would say, now that SIDH is dead, SKISign, which stands for short quaternion and isogeny signature. This is a signature scheme. It is still based on supersingularity curves, isogeny graphs of supersingularity curves, etc. But it uses a different way of looking at things still. It is currently today the most compact signature scheme, credibly post-quantum, and still credibly post-quantum, among all signature schemes, among all post-quantum signature schemes that we know, in or out of the NIST competition. And it is like 5 to 6 times smaller than Falcon, which is currently the most compact signature that's going to be standardized. So again, this is low, but one strong selling argument, and this is even more interesting for signatures than for public key encryption. If you take the size of public key and signature combined, these are the things that typically you store in a certificate, TLS certificate. So if you have a chain of certificates, you may have to store 4 or 5 of these pairs. So having something that's 5 times as small makes automatically your certificate 5 times as small. And this may be an interesting game. For example, let's say now you want to migrate Bitcoin to post-quantum security. Bitcoin is using ECDSA signatures. If you go to Falcon, you will suddenly have your blockchain that blows by 5 times. And you know that the Bitcoin blockchain, just to store it, takes a... Talking too much, not clicking enough. Oops, sorry. So if you instead use SKISign, you have an opportunity. What's happening again? Do I have to insert my password or? Yeah. Oh, there it comes. Should have deactivated the screensaver. Sorry. So yeah, I will say if you replace ECDSA with SKISign in Bitcoin, you will get something that's only twice as large, even a little bit less. Yes.
PDFs can be constructed through discrete log, I think, right? So what's the purpose of using the isogenies?
VDFs. So VDFs is not about the discrete log. It's not based on discrete log. It's different problems, but they can be constructed on groups of unknown order. That's true. It's for VDFs is just another way of doing it. You can say just, yeah, via diversification. You have something else. It's different. It's interesting. Technically, if you look at the details, we can have a chat later. What are the advantages and disadvantages of using isogenies for the VDFs? It compares in an interesting way to the proposals based on groups. Actually, I would argue that the most interesting thing about this, something that was published 1 year later, or 2, was it Eurocrypt 2020 or 2021? Something that's called delay encryption. This is a primitive that's more powerful than VDFs. And it's currently known, we only know how to instantiate it from isogenies. There is no other equivalent. And that's something that, unfortunately, we don't know how to, it's complicated. It's not something that I would call practical to these days. But if it was practical, there would be already blockchains using it. So maybe it's a good thing that it's not practical yet.
So is there an abstraction for, they seem to give you something algebraically that's more. So is there an abstraction for isogenies? Like in
this case, it's very easy to abstract. You can understand it as a slight generalization of pairings. This is something that you can manipulate without knowing almost anything about isogenies. C-side is the same. C-side is usually explained in terms of group actions. So you don't need to know what's an isogeny. You just need to know what's a group action, and you can manipulate it. SKISign, it's a mess. You need top experts. Like it's tough even for us in this room, and we are the top experts. So yeah, there is not an easy abstraction for anything isogeny, but some of these, at least of these families of schemes like C-side, they can be manipulated quite easily and conveniently. And so, yeah, coming of age this summer, big celebration, big time. Psych is selected to the 4th round of the NIST competition. Psych is an alternate finalist. Everyone is believing very strongly that sure, lattices go first, because of course lattices go first. But soon isogenies will be in every single mobile phone. And of course, you can see how a company that invests a lot in post-quantum research likes to celebrate things and make press releases. Before even we had the time to make a press release, I received this email by Craig, my psych co-author. I was lecturing in Edinburgh at the time, and then I just opened my email and say, hey, David, Luca, please connect as soon as possible on Slack and see the messages there, which of course I did. The rest is history. If you don't know the history, I strongly recommend this Quanta Magazine article, which is very nice, except for the clickbait title. Because who cares that it was cracked on a laptop? Could have been a mobile phone, could have been a cluster. It's not very important. Yeah, you heard the news. Psych was broken with a classical algorithm and even a practical algorithm. So there was no doubt. Like, it was very easy immediately to recognize the power of the algorithm, because I mean, the authors, Thomas and Wouter, with the announcement, with the email, with the message saying, hey, we have an algorithm, they also send the solutions to the psych challenges. So we had no reason to doubt that they had something quite interesting. And the algorithm is very beautiful. I'm not going to explain it. It's complicated mathematics, even higher mathematics than what you usually use in isogeny-based cryptography, but it's very elegant. And actually, the fact that it was cracked on a laptop, it's something that's promising, because these algorithms are so efficient that maybe they even have constructive applications, not only cryptanalysis. Because if you can, like with the recent refinements, the attack runs in seconds, and you can hope that maybe these algorithms can be used to construct new things from them. Then, of course, what does a company that has invested on post-quantum security and made press release, make marketing out of it? Well, of course, it just adjusts the press release. And it was good. I got my bonus before the attack. So why are we here in this room? Is all isogeny-based crypto dead? Why are we even talking about this? Is it just some showing some vacation family pictures? Just say, oh, it was the good times, how fun it was. No, there is still things. There are still things to do. And the reason we are here in this room can be summarized in this website that pretty quickly we put up together with the help of Giacomo Pope. Trying to map the space of what's out there, what's broken, what's not broken. Oops, sorry, Francisco. So let me go to where it is. There. This is what the website looks like. So as you can see, it's incomplete, first of all. It's wrong. There are some things which, there are some bugs which I must fix, but everything is tracked on GitHub. So if you see problems or if you want to add information, you can make pull requests or just open issues. I have a few that are in the queue that I should push to the GitHub repo. The idea is to have a list of the schemes that, or at least the most interesting schemes out there that have been defined from isogenies, a list of the assumptions they're based on, and a list of the attacks, the known attacks on the assumptions. And then, as you can see, the color codes: red means it's broken, red means polynomial time, green means exponential time, yellow means sub-exponential time, and then there is one column for classical, one column for quantum. And you can see there is some red. There definitely is some red. Some things are broken. SIDH, psych, B-side, SIDH, proof of knowledge. These kind of things, they are all broken. Some other things are green. Some other things are orange, but we always knew they were orange. Like, this is no news. It's not a consequence of this summer's attacks. This is something that I can explain a little bit more in detail. So, yeah. As you can see, the field is not completely broken. It's not completely dead. There is some there is something more to say about isogeny-based cryptography. It has not said its last words. And of course, what does it mean? Like, what are you telling Luca? Like, sure, maybe not everything has been broken, but is everything going to be broken in 1 month from now, in 1 year from now? And of course, I don't have the answer to this. I don't know if people will find new algorithms. But things have stabilized a little bit after the summer. And now we get a better understanding of how the attack worked and what kind of information it was using and what the power was. And it's become pretty clear that the attack was essentially only affecting SIDH, psych, and related schemes. So those other schemes you saw in red, B-sides, and other schemes that were essentially based on the same assumption were broken. But this attack is using, in a very central way, some information that was specific to SIDH. And now I'm going to explain what this kind of information is. And we don't see an easy path of generalizing this precise attack to other schemes. So if we want to make a chart of the assumptions, maybe more visually useful than the website that I just showed to you, is trying to arrange the problems and the cryptanalytic problems that we study along two axes. These are the most important two axes. One is what people call the torsion knowledge. And one is the knowledge of, I write here, and E. You should read this as endomorphism ring. And now I'll explain what I mean by these two terms. And now, along these two axes do not explain everything about the assumption that we use in isogeny-based cryptography. Of course, there's a plethora of assumptions, because like the same way that you have discrete log, but then you have Diffie-Hellman, decisional Diffie-Hellman, computational Diffie-Hellman, you will have the same kind of things here. You will have SIDH, decisional SIDH, computational SIDH, all those things. But here it's more, this chart is more for cryptanalysts, not for cryptographers. This chart is, of course, CDH, DDH, in the end, what do? You always apply a discrete log computation to solve CDH or to solve DDH. What counts here, this chart is just to try and map the space of algorithms that we know and what's the power of algorithms. And so where do things sit in this chart? And now in the little time that I have left, I will try to explain what the y-axis means, what the x-axis means, and then I will magically make scheme appear here. So I will go to the drawing board. Just a second. Okay, let's see how good I am. So I showed you two axes. One is the torsion axis. Let's start with that one, because it's the one that's easier to explain. So there was one thing that I told you in the beginning. Remember degree, this thing, this magic thing, this magic number associated to an isogeny. So when you think of an isogeny, you should think of it as a polynomial. It's not very different. What I showed you was a rational fraction. It was x squared minus 1 divided by x. So it's just a bunch of polynomials. And the degree of an isogeny is more or less the same thing as the degree of a polynomial. So the larger the degree of an isogeny, the more information you need to store this isogeny. That's a pretty accurate description of what the degree is. And this means in particular that we can only manipulate isogenies of small degree. And if this is what we call an L isogeny, this is an isogeny of degree L. And it is interesting to look, for example, at analytic curve E and ask ourselves, what are the isogenies of degree L that start from E? And then you will realize that there are a most, so let's say I'm going to L equal 2, for example, classical example, you will realize that there are a most L plus 1 isogenies starting from E. And then you can go on and look, okay, let's look at these three curves that I've reached. How many isogenies? Again, there will be a plus, at most L plus 1 isogenies. And you can keep going. If you order complex numbers, this is actually the only thing you see. You will just see an infinite tree spanning forever and forever of, in this case, L equal to a 3 regular graph that goes to infinity. Not a very interesting picture. But we are over finite field, of course, and so this picture will become something more interesting. So the first thing that can happen is that maybe not all of these isogenies are defined over the finite field. It may happen that some of these isogenies only exist over an extension field. And so a very typical picture will be something like this, just a cycle. Most L isogeny graphs of ordinary curves, actually 50% of the L isogeny graphs of ordinary curves look like a cycle. Simple structure, we all understand it. This is the basis of, for example, the schemes that were proposed by Couvain, Rostov, and Stolbola. But another thing that can happen, and this is what happens for supersingularity curves, so is that you get something that's L+1 regular. And now, of course, it becomes tricky to draw something that's L+1 regular, because at some point I must have loops that form in this graph. I didn't define what it means to be supersingular, what it means to be ordinary. I don't need it, because actually the shape of the graph is a good enough definition of supersingular ordinary. There are some families of curves which we call supersingular. They are exactly those for which the L isogeny graphs are L+1 regular. And there are other families of curves which we call ordinary, for which the generic shape of the graph will be a cycle. Let me show to you some supersingular isogeny graph. Where is it? Go here. Okay, much better than anything I could do with my bare hands, with my stylus. Here, each node, each dot represents an elliptic curve up to isomorphism. Never mind. Each edge represents an isogeny of degree 2. In this case, this is the 2 isogeny graph of the supersingular curves defined over some finite field with of characteristic roughly 1,000. It must be 1,031. As you can see, it looks 3 regular, although there are some strange things sometimes. So for example, here you can see a loop. But if you look closely at this loop, it's like if you count things appropriately with multiplicities, it is still 3 regular. So this is the typical example of an isogeny graph that we use, for example. This is the graphs that Charles Gore and Lothar suggested to use for defining hash function. So what does the hash function look like? Well, it's very simple. Just fix some starting vertex. I don't know, this one, for example, and then define the hash function as in any arbitrary deterministic way, take a random walk. So like, I don't know, start in this direction. And then if you want to hash the string 0, 1, 0, 1, well, take 0, 1, 0, 1, and then the elliptic curve you end up in is going to be your hash value. So this is what what they define as a hash function. Now, the only thing that you must imagine is that in practice, what we use in cryptography is not these small graphs which fit in a slide. We're going to use graphs over exponentially large finite fields of characteristic roughly 2 power 200, power 2 power 500. So large finite fields, and these graphs will be as large. There will be an exponential number of nodes, more than the atoms of the universe, if you like, and they won't fit in a slide. I cannot show them to you. So imagine these huge graphs, and imagine that crypto is happening in these huge graphs. Yes?
Finding a loop would create a collision.
Finding a loop creates a collision and is related to this endomorphism dimension that I had, my x-axis, and actually we will discuss that. Finding loops. Loops are rare. We can even bound the number of loops of any length. So like a one loop, there's only going to be a few in the graph. And then for any length, for any cycle length, we can bound how many cycles of that length there are in the graph. Yes.
In your original definition, isogeny was something directly going from one thing to another.
True.
Where has the direction disappeared here?
The direction has disappeared. There is a little bit of trickery, but there is a theorem that I haven't given to you. That's called the dual isogeny theorem. It's a pretty basic result. It's one of the first results you encounter when you study isogenies that tells you that whenever you have an isogeny of degree L going from some curve to some other elliptic curve, you have something that's called the dual isogeny that goes from the arrival elliptic curve to the start elliptic curve, so that goes back, and that has the same degree. So that way, it's just more convenient to not draw both isogeny, just see the graph as undirected. Sometimes, and these are not graphs, these are actually multigraphs. Some edges must be counted with multiplicities, and the multiplicities may not match in the two directions. So there is a little bit of nastiness to handle, but there is at most two nodes in the graph that have this nastiness, and we know how to handle them. So we usually just draw them undirected and don't waste time counting multiplicities. Other questions? Okay. Ah. Oh, no, don't do this. Forgot that. Okay, so what is this torsion axis that I mentioned to you? Let's get quickly to the conclusion of this talk. My general isogeny problem will look like something like this. I have some starting curve E0, I have some arrival curve E, and me, the attacker, my goal is to find a path in some isogeny graph. Which isogeny graph will depend on exactly what system we're talking about, but it will be to find some path in the isogeny graph that links E0 to E. And this path in the graph will correspond to a sequence of isogenies of degree L, for example, so a sequence of L isogenies. And this sequence of isogeny, if you compose them, the same way that you can compose polynomials, will be an isogeny of degree, the product of the individual degrees you find along the way. So typically, for example, if we find a path in the two isogeny graph, and if this path has length n, the composition of these n steps will be an isogeny of degree 2 power n. The same way that the composition of n polynomials of degree 2 is a polynomial of degree 2 power n. So this is my goal, and this is a hard problem in general. This is a problem that we believe to be hard, that we've been studying since the 90s, since these beginnings that I mentioned to you, before we were even talking about isogeny-based cryptography, when we were interested in discrete log cryptography and reducing the discrete log. We realized that, sure, an isogeny can be used to reduce the discrete log from one curve to another, but in general, it's not easy to find these isogeny paths between two elliptic curves. But now, so how are these elliptic curves given? Typically, they will be given by some equation. So for example, this could be y squared equals x cubed plus x, the every isogenista favored elliptic curve. And this one will be some other curve, y squared equals x cubed plus ax plus b, just the arbitrary curve. Okay. Typically, the problems are usually of this type, where one of the curves is fixed, it's always the same, and the other one, E, is going to vary and be a random elliptic. But maybe sometimes, and it happens often, actually, maybe sometimes you have some point P in the elliptic curve, capital P, some coordinates U and V, and you know the image of the point by the isogeny. Like P equals some U prime, V prime, let's say. Okay, you have this extra information about one point on the elliptic curve and its image. Okay. This is certainly more information than just the equations of the curves. Can you exploit this information? That's a legitimate question. And so usually what happens even is that you will look at points. Your question should be, your first starting point should be, what's the order of E0 over FP? For example, let's call this. Let's call this Q, because it's not going to be necessarily a prime. So let's call N the order of this elliptic curve. Then maybe I have some points P of order dividing N. These are points such that when does everyone know what order of a point means? Raise your hand if you know what order of P means. Okay, okay, looks good. Lots of hands raised. So yeah, this means that if I multiply the points by n, I will get the identity element of my group. Okay. In general, when you do, if you're used to elliptic curve cryptography, you will know that your elliptic curve, the typical elliptic curves you work with in elliptic curve cryptography have cyclic structure. Okay, will be something like this, will be isomorphic to, yeah, I should write isomorphic. Will be isomorphic to some cyclic group of order n, and usually n will be a prime over or a multipolar prime. But in isogeny-based cryptography, it's more common to have something like this. Okay, so a product of two cyclic groups. And then the most interesting problem, I need a new page. Where is it? There. The most interesting problem will be, let's rephrase things again. I will get E0, I will get P and Q, two generators of the subgroup of order n for my elliptic curve. And I will get E, I will get phi of P, phi of Q, and my question will be find phi. Okay. This is one problem that often happens in practice, and this is exactly the SIDH problem. I haven't explained to you why this problem. To understand why this problem is the problem SIDH is based on, you must look at how the key exchange works. But for technical reasons, when you have an SIDH instance, when you have an SIDH public key, the kind of information that you get is some start curve, some arrival curve, some points P and Q of order n, and their images under the secret isogeny. So now think again about polynomials. If I have a polynomial that I'm looking for, and I know how the polynomial acts on some group of points, I can interpolate this polynomial. And this is exactly the same kind of information that you have here. You could, in principle, say, well, an isogeny is not different from a polynomial. I know this n is going to be large. This n is going to be very large. You really know the information on a lot of points, much larger than the degree of the isogeny, actually. And so you may say, well, I have enough information to interpolate the isogeny. And you would be exactly right. This has always been known, that the statement of the problem has enough information to interpolate the isogeny. But because the isogenies involved in SIDH have large degree, for a long time we thought that even with this power, even with this information, there wasn't enough things to hang to, and it was still difficult to compute this isogeny. So this is the torsion axis, the y-axis that I had in my diagram. It was maybe in your information, in your definition of your problem to solve, in your isogeny problem definition, there is more than just the start curve and the arrival curve. There is also some points of some order and some information on how the isogeny acts on these points. And so the most possible information that you can have can be the action on the whole torsion. And maybe sometimes you, instead of having the action on the whole torsion, you only have the action on one point. Okay, so that's half as much information in a sense, square root as much information, depending on how you count things. So all these things are families of problems of isogenies with torsion point information. And so this is the x-axis of my diagram. And now there is the y-axis, which I need to define very quickly, which is the endomorphism ring axis. So what's an endomorphism? An endomorphism is an isogeny from a curve to itself. Endomorphisms, for example, you have one easy example, multiplication by m. This is a map that goes from E to itself, sends the point P to m times the point P. It's an isogeny, it's a group morphism, it's an endomorphism. So certainly for each integer m, you will have a corresponding endomorphism, which means that you can identify the endomorphisms of E with some larger set that contains the integers. Certainly will contain the integers. But there may be more, there usually is more, and all endomorphisms of elliptic curves, all endomorphisms of elliptic curves will look something like some endomorphism omega inside the endomorphism ring of E, with the property that omega satisfies an equation such that omega square plus T omega plus delta equal to 0. So what I mean by this, what I mean by omega square, this is the same thing as omega compose omega. So just apply the endomorphism twice. This is the same thing as apply multiplication by T. So apply omega and then multiply by T, or the other way around. Okay, so this is multiplication by T, and this is multiplication by delta. Okay, so this means that endomorphisms will behave like quadratic numbers. Like if you're familiar with quadratic number fields, this is what an endomorphism will look like. And so, for example, the endomorphism ring may be something like this: a two-dimensional, a rank 2 lattice inside the two-dimensional vector space. Okay? This is the case that we call the ordinary case, connected to those ordinary elliptic curves. And then sometimes, and this is the usual case for elliptic curves for supersingular elliptic curves, you will have that the endomorphism ring is isomorphic to some structure, Z plus iota times Z plus J, I'll call this I times Z, J times Z plus IJ times Z, where these IJ are both endomorphisms and satisfy something like y square equals minus A, J square equals minus B, and IJ equals minus JI. Okay, very strange sorts of things that can happen in the endomorphism ring of an elliptic curve, where essentially you're identifying endomorphisms with quadratic numbers, and plus some endomorphisms do not commute. In general, you shouldn't expect endomorphisms to commute, but they anti-commute. So if I first apply one endomorphism I and then apply one endomorphism J, is the same thing as applying first J, then I, and then swapping the sign of my point. Okay, this is what we call quaternion algebras, and this is the usual case. And so the x-axis, my knowledge, my endomorphism ring knowledge, is explaining how much do I know about the endomorphism ring of my elliptic curve. I always know that the endomorphism ring of my elliptic curve will contain something like Z, will contain the integers, will contain this part. Okay, so this is, now if I go back here, this is what I mean by non-information. If all the information I have is that Z is contained in the endomorphism ring, well, this is trivial information. This is what I mean by non. Sometimes, where is it? It's here. Sometimes I will know something like this. I will know, of course, that Z is contained, but we will also know one endomorphism omega, and this is what we call an orientation. Don't really have the time to go into why this is called an orientation. You need to see more pictures to see where the orientation comes from. But so sometimes you have these supersingular elliptic curves with endomorphism ring, which is a rank 4 lattice, but you only know a rank 2 sublattice of this full lattice. And so this is what I call here the orientation case. And full case is where you know all the endomorphism ring of the elliptic curve. And there, final slide, here is the picture. So what do we know today? We know that, so now just if you look at the knowledge of the endomorphism ring of that arrival curve, we suppose that the start curve is 0, is always known in the endomorphism ring. It simplifies the picture. And how much do you know about the torsion? So if you know the action on a full torsion subgroup, so you have a basis of some large enough torsion subgroup, and you know its image under some secret isogeny, without needing to know the endomorphism ring of the arrival curve, you can find the secret isogeny. This is SIDH, this is what's broken. What we also have been known for forever, essentially, but it was only formally proven without heuristics by Benjamin Wesolowski just 1 year ago, is that if you know everything about the endomorphism ring of E, then you can find the isogeny that goes to E, any isogeny that goes to E. So this is a reduction that shows that computing endomorphism rings or finding isogeny walks in an isogeny graph are equivalent problems. There is a polynomial time reduction that holds only assuming the generalized Riemann hypothesis. So this means that you cannot instantiate a problem, a cryptosystem, if the knowledge of the endomorphism ring of all the curves is given. And so, of course, like this zone, just stay away from it. You shouldn't instantiate your problems if the endomorphism rings are known. You shouldn't instantiate them if the full torsion information is given. Of course, there are parameters there. If it is a small amount of torsion information, it won't be enough. You need to have more than the degree of the secret isogeny torsion to say something non-trivial. And then there is the rest that is still considered safe. So here there is a great area where actually this can never happen. If you have an orientation, automatically you have some partial information on the torsion, something that's represented, like, do not look at the picture. Like, this is only for those who were in the private seminars that we had this week. But so in this case, when you know one endomorphism, you automatically know some partial torsion information. And in this case here, this is in orange, because these schemes are believed so far to be exponentially secure against classical attacks, but only sub-exponentially secure against quantum attacks. So these are a sort of midway thing between post-quantum and pre-quantum, which are nevertheless very interesting because they enable lots of applications which we don't know how to do in any other way than using these kind of schemes. Here you have weakenings of the SIDH problem. For example, you have signatures based on SIDH. They're actually based on some torsion problem where we have much less information on the full torsion, an assumption that's usually called the SSP in the literature. This is still considered to be safe. And actually, there is something that's not published yet, but will soon. There is a reduction between these two kinds of torsion structures, which I know I didn't explain what they are, but that shows that essentially you should believe these things to be as safe as these things. Like if you believe this is safe, you believe this is safe. And then in the lower left corner, you have ski sign, this famous signature, which I said is going to be the herald of isogeny-based cryptography in the next years, which, as far as we know, modulo some technical details very complicated, has no torsion information and no endomorphism ring information given to the attacker. And so it's here it should be the safest among all these problems. So will the next year bring improvements to these attacks? If they have to come, these improvements will not be just in the form of a generalization of these attacks. I think we need new ideas to advance this red line to cancel other things. It may happen. I have no way of saying no isogeny-based crypto is going to be secure in the next years. No one has for any branch of cryptography, but we are eager to find out. And as long as we still have green things here, we will keep doing research in isogeny-based cryptography, and I invite you to join the efforts and learn more about it. Thank you very much for your attention. Sorry for being a bit over time.
So thank you. We have time for one quick question, maybe two. Questions?
Emanuele has one question. Yep. Shut down the camera. Cut Zoom. We are thinking about it. Yeah. If we don't do it, maybe someone else will do it, but we're thinking about it. Yes, Joachim.
If you had a really brilliant master student and he wanted to do a PhD thesis somewhere in this area, so something doable, probably, but not trivial. What kind of area of question.
Depends. CS or math?
Hmm?
CS student or math student?
No, I'd say as a math student.
Yeah. Because of course the field is large, and this is quite different from when you look, for example, at discrete log based crypto. Discrete log based crypto, you have essentially one assumption is discrete logarithm. You break that, you break all the crypto, and then well, maybe you have some variation with the pairing based cryptography, which is somewhat related but not totally. But here you really have a zoo of different ways to construct isogenies, and they lead to very different things. So for example, if now answering on what you were not asking, answering more on the CS side, definitely there's lots of students who are working on with the C side, because as Jean-Paul was asking just earlier, is there an abstraction for these isogenies? In the case of C side, and this thing's called Scallop, which is a recent preprint, a recently published paper that does something similar to C side. So in this case here, it's very easy to manipulate these things without understanding anything about isogenies. You can really do crypto with these schemes like you were doing crypto with discrete log before, without having to understand the analytic curves. 80% of cryptographers don't understand anything about algebraic geometry, but they understand very well cyclic groups and reductions and algorithmic things. And so they are very eager to work with discrete logarithm systems because they can construct crazy things. It's amazing the amount of schemes, different schemes that you can construct just by based on one single thing. So for those students, this is certainly a very fertile area where ideas keep coming, and they are very easy to present without needing the number theory and the algebraic geometry jargon. And so they're also easy to disseminate.
What you say, variations of PK-Harman with additional properties and so on.
Yeah, maybe less properties than yeah, they have fewer properties, and thus they are supposedly post-quantum half secure. Yeah, so that's definitely a very fertile field where things are happening. Things keep happening all the time. Then there is the rest of the field where things can become complicated because there is no way to explain ski sign in simple terms. We spent more than one day this week explaining it at different level of detail. And here there are lots of questions for those who are more into the implementation side of things. Like, okay, I have this theoretical scheme that's described in terms of quaternions and isogenies. Now I need to put into software. This has already been done, but it's a mess. Can I do it better? Can I find better algorithms? And there are so many sub-steps here that it's also going to be very fertile just to think about how to improve these things. Here we're talking about signatures that can sign in hundreds of milliseconds. This is not fast. So certainly there's going to be lots of work in the next years, especially if someone, I don't know who, submits key sign to NIST. There's going to be lots of interest in making this faster for signing and for verifying. So this is also very fertile for students who are more inclined towards implementation algorithmic side of things. And then there are the fundamental questions like, how are these the generic endomorphism ring problem? Also, what can I do with these new attacks? I have these new attacks on SIDH. They are based on abelian surfaces. They go to more general objects. What's their power? Can they be used to construct more schemes? This is also extremely fertile. Tougher maybe, because it's not easy to come with new schemes. We've been very lucky these years, but also the field was fresh and there was lots of things to discover. Of course, as we progress, finding new things becomes harder, supposedly, but we don't seem to stop. We keep finding things. So it's also quite interesting now to think, yeah, does this give me more power to do more things? And then, yeah, there's lots of things, and certainly you have to adjust to the student. And so if you have a precise student in mind, just send him to me, send her to me, and we can see what's an appropriate problem for him or her.
Maybe less. Yeah.
What's the potential of isogenies versus ellipses?
Potential. There are so many dimensions in which this question can be asked and answered. Let's talk about potential in the real world. Where do you see isogenies being used in the real world? Maybe is that what close to what you meant? What's the advantage?
Yeah.
Well, the advantage is clearly, well, there's several. Here's key sign, the advantage is going to be small signatures and public keys. This is something that it's undebatable, unless someone finds better, like shorter, more compact lattice-based signatures. But this is clearly useful in public key infrastructures, blockchains, all these things where you really need to store lots of signature public key pairs. So this is clear, it's a clear advantage, and the clear disadvantage is the speed. This is very, very slow, both in signing and verification, although verification is acceptably better than signing. Another advantage, for example, here, CSIDH, this thing is reputed to be the only usable non-interactive key exchange with some level of post-quantum security. So this is a primitive that's useful, for example, in TLS key establishment sometime, or in other contexts where you need non-interactive key exchange. So this is one other selling point for CSIDH, for example, CSIDH or Scallop, if you wish. Threshold signatures. These are other things that you can construct mostly from Scallop and from some special cases of CSIDH. So in a way, essentially, this family, this one is the one, remember that I told you, it's the one that's easy to abstract. You don't need to understand much about the isogenies. This one is the one that, because of its closeness to discrete log, just in the way you present things, this group action framework, it enables a lot of things that look quite similar to what you were used to do with discrete log. For example, the threshold schemes come from just applying the Shamir interpolation in the exponents trick. So you can translate that to this setting, and it works nicely, and that's how you get the power. So in that way, it is more flexible than lattices for some specific problems. In other ways, it is less flexible. For example, we have no idea of how to make even simply homomorphic schemes based on isogenies, and we really don't believe that's a possibility. So of course, FHE is something that's super flexible when you look at it. And this is not something that you can hope to get from isogenies. That's fine.
Last question. Okay. Anyone has any more question? No? Okay, in that case, thanks to speaker again.
Thank you very much.